Let's get started here with some basics about how light works. This is going to get soft scientific. I'm not going to go too much into the weeds. And trust me, there are weeds here. There's a lot of detail you can go into about how light interacts with surfaces. But I'm going to try to give you the simplified and focused version that I believe is useful and pertinent to modeling and shading in particular. Here's our light bulb. Very fancy. It emits light. Light comes out of something like a light bulb in photons, all right? We're not scientists. I'm not a scientist. I don't know what a photon really is. You don't know what a photon really is. Are they particles? Are they waves? Go to Caltech and get a degree in it. But for our purposes as artists, we want to think of photons as particles that shoot out of a light source and that are generally evenly distributed. In something like a light bulb, we're saying that it is generally emitting light in all directions at the same intensity. It's not more intense on the right side of the light bulb or more intense on the left side of the light bulb. It's the same intensity on all sides as it's emitting. And now, like I said, this is a concession. We're doing this to understand this as artists. We're going to say that it emits an equal amount of evenly distributed photons in all directions. So what does that mean for us? This would be considered a point light source. Now we can also have let's do a directional light source. So we might think of this like a spotlight. This is a simplified spotlight here in that realistically a spotlight has some spread, but let's say that it shoots out its beams parallel. They stay straight. The sun is also like this. So the sun is technically a giant light bulb. So it's technically one giant light bulb style point light source, but it is so big in comparison to the size of the Earth that for all intents and purposes, we consider that its photons, its rays of light, reach us parallel, that there's no divergence. Realistically, in truth, there actually is some divergence, but for all intents and purposes, we will pretend that there isn't. And the other kind of light source are area lights. And we can consider these for our use here, soft lights. So this would be something like a photographer's softbox or an open window without direct sunlight coming through, just a window that's open to the sky. It's a wide, broad aperture that is emitting light in a general direction. The interesting thing about this, and this is a detail that we might get into later, is that soft lights are diffuse generally. So they're not just shooting out straight down like a spotlight. They're actually kind of spreading photons in all sorts of directions, which obfuscates the clear delineation of the shadows and the clear direction of the light. So this is advanced, especially for something like shading in pencil. This is more typical, but also requires some special considerations for mapping the spread of shadows because the light photons are always kind of diverging. And the directional / parallel light source like the sun, the directional / parallel light source like the sun is generally, this is more what we will work with as artists, and especially in a medium like pencil drawing, monochrome rendering, where we usually are going to focus on one light instead of multiple light sources. For the sake of making our drawings clear, we're generally going to work with this. Let us move on to talking about how these lovely photons interact with a surface on the most pertinent and basic shape, the sphere. So let us put a sphere here. And let's imagine that it is sitting on a table and that our eye is right down on the edge of the table and we're just looking at this sphere perfectly side on. Now this sphere, let us imagine that this spotlight that we drew up here is big enough that it will light up the whole sphere, right? But let's imagine these directional parallel photons hitting this sphere, right? So first, let's map what that would look like at the edges. If this parallel directional light source is directly above the sphere, perfect 90 degrees above it, and we're looking at it from the side, then that means that photons at the edge of the sphere will be catching it right at its edges. And that point of tangency is going to be right in the middle of the sphere. Let's get another one on this side. And the other point of tangency, boom, there. So let's say that these are photons. These two that are hitting on the edges are photons, and we know there's other photons coming down here and outside it. But that means that the cast shadow of the sphere, we wouldn't be seeing it perfectly side on, but I'm just going to darken here to indicate to us that this is where the cast shadow is going to be directly under the sphere and the same size as the width of the sphere, because these light photons are coming in parallel. So cast shadow. This means that right down the center of the sphere's body would be what we call the terminator or the core shadow. So the terminator or the core shadow is the exact spot where the light ends and the shadow begins. So that is the terminator, i.e. where the light terminates, / core shadow. Now, for now, we are going to think of this in a very binary way. So on this sphere right now, there is either light or there is shadow, and we're not going to think about anything else. There's other parts of the light. We will get to them. For now, we are only going to consider light and shadow. So let's say that this is all shadow. There's other effects in reality going on here, reflected light and occlusion, but I only want you to think in the binary of is it in light or is it in shadow right now. The terminator is where the light stops and the shadow begins. Everything below it in this case is shadow. And the light is the only part that is being affected directly by first strike photons hitting it. So let's assess now what is happening with these other photons that are coming down and hitting the light side. So remember, we're assuming that photons coming from a light source are evenly distributed. They're not more dense in one part of the light ray or another. So here, let's assume that I got these spacings exactly right. So we got 1, 2, 3, 4, 5, 6, 7 photons coming in that are not going to be in the shadow side, right? That are not going to be producing the terminator. So let us drop these down. So again, let us assume that these are all evenly spaced. So these photons are striking the sphere. Here in this diagram is contained the secret to shading. This is it right here. The main thing I need you to notice is the difference in surface area on the sphere between this area along the edges of the shape and this area near the top of the shape. Clearly, in respect to the evenly distributed photons that are striking this ball, this area on the surface of the sphere is much smaller than this area. This area gets long. Now, each photon we're going to assume, and this is generally correct, that each photon contains an equal amount of light energy, right? Whatever that amount is. Let's say that the amount of light energy that each photon contains is, I don't even know how to measure it. It's 30 watts, 1,000,000 watts, 1,000 watts. It doesn't matter. For our purposes, all that matters is that they're equal. So this photon, which contains the same amount of energy as this photon, has a larger surface area of sphere surface to illuminate with that same amount of light energy than this does, right? If they contain the same amount of light, these two photons have less area of sphere to illuminate between the light energy that they have than this guy and the photon at the edge, right? They have to illuminate a larger surface area with the same amount of light energy. And that is why things shade in the light. That is why there is shading on the light side of a form. That is why things get darker as they approach the terminator, the core shadow. This also leads us to one of the most overlooked and important things about modeling, rendering, and shading your artwork. And that is that the fall off of light in the light side is not linear. It is exponential, right? So up here, the spacing between the photons is equal, right? The way that coming in directly from above and with no divergence in their angles, they're equally spaced, but because of their interaction with this curving form, the difference in the amount of light that is lost here and here is not linear, it's exponential. It's a much bigger shading difference here, closer to the edges, than it is up top. And that is the reason, that is the scientific reason why values, that is to say, shading, right? Values just means lightening or darkening, or areas or patches of light or dark and the relative difference between them. Values are compressed in the light. Another way to say that is most of the shading in the light occurs close to the core shadow. And when I say most, there's actually a real mathematical number for what percentage of the light fall off occurs in what percentage of the form turning. I don't remember that number right now, and it's not actually useful for an artist. You're not going to replicate it exactly, and just because you got it right doesn't mean that it would look good. But generally, when I say most, it's about 60% of the shading. To be more accurate, value change occurs near the, let's call it for now, just we're going to say occurs near the core shadow. That's not actually super useful for us. For artists, all you need to do, you need to keep this in mind. The values are compressed in the light because most of the value change is going to occur closer to the core shadow, and less of the value change is going to occur as you go further up towards the light source. And that, so that means that the vast majority of the shading that you're going to apply is going to happen near the core shadow. You want it to be de-emphasized as you get up near the top. So to drive the point home, Instead of these diagonal hatch marks to indicate the shadow, I'm going to say that these vertical hatch marks indicate what we're going to call the halftone. So you can see that the halftone is quite small. It takes up a much smaller area of the light side of the sphere than the open, what we're going to call main light. There's tons of words for this main lit area of the shadow. The vocabulary in art has never gotten quite codified, so you hear a lot of things. We can call it the main light. It has other names like the center light or the local tone, but we're just going to call it the main light area. In the main light, there is going to be barely any change in value. And in the halftone is going to have most of the value change. Honestly, the more you keep the value changes really strictly in the halftone area, that blend between the halftone and the terminator, generally, the better, more organized, the more graceful, and more formy your pieces are going to look. And the more that you shove value change into the main light, the more it's going to look over-rendered. It's going to look over-modeled. It's not going to have the correct contrast hierarchy, which is what we're going to go into next. But before we leave this, let's just indicate the very basics of what happens in the shadow. But honestly, what happens in the shadow is you want it to be very subordinated. You want it to be super simplified, and you want it to be very low contrast. So all you need to know is that obviously, like we said, this directional light that we're imagining it's bigger than the ball. So there are other photons coming in that are striking the ground over here, right? So a photon strikes the ground here next to the ball, and photons will then scatter in multiple directions, depending on the surface that the table is, right? If it's a mirror, they actually won't scatter in all directions. They'll scatter very specifically. But on a general surface, there's going to be some bumpiness microscopically on the surface. So light will scatter, boop, 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 all directions. And that will bounce back up into the shadow side of the ball. So this will have the effect of making the core shadow look darker by contrast, make it stand out more, as I'm sure you've seen in well-rendered pieces of art. Because the main body of the shadow is getting pumped up a little bit, being illuminated slightly by the bounce light that is coming from these photons that are striking the environment around it. And this can actually become very complicated. For example, when you're outdoors and you're looking at, when a ball is outdoors, when any shape is outdoors, there's things bouncing, hitting, spreading color and light around everywhere, absolutely everywhere. So this can actually become extremely complicated when you're outdoors, but we are imagining a very simplified studio setup here. So light will bounce up here, which will give the effect of darkening the terminator. I'm going to imply that by doing some cross-hatching up underneath the terminator. So that is just to imply that as you approach the terminator, right, as the shadow moves closer to the terminator, it too gets darker and it is more light in this main body. There is another area where the shadow darkens, and that is down here where the ball touches the table. This is the occlusion shadow. So let me just imply it here with more cross-hatching. So this is the occlusion / contact shadow. Occlusion is the fancy word. That is a shadow that is created by the occlusion, that is to say the hiding or blocking of light, right? So these light rays, they just can't bounce into this little corner very well. So things get very dark very quickly. But you can just think of it as a contact shadow. The occlusion happens as a dark accent wherever things touch, right? So if I hold my fingers there, you can see the crease between them gets darker than anything around them. Or if I, make that hole between my hands, it's dark in there because light is getting in there, but it's going in, bouncing around. Every time that it bounces, it loses energy, right? That's another point to keep in mind about these photons. Every time they strike something and bounce off to go hit something else, they lose a lot of energy. And that even actually affects their color, which is a discussion for another video, but it has a lot of effects. So light is getting into that hole, but it's going in there and bouncing around so many times and finding it losing so much energy by the time it comes back out and hits your eye / the camera that it basically looks black or darker than everything else that's in there. There's some light because if I put my eye, my very advanced human eye, right up to the hole and let my pupil dilate and adjust so I can take in more light, I can still see in there. I can make out some detail. So that means that stuff is bouncing around and some light is getting back out. But that is the contact shadow. Now, those are the main parts of the light on a basic matte, that is to say not shiny, for example, white ball, right? This ball could be any color, but let's just say it's not shiny. We're only dealing with it's like a rubber tennis, it's like a rubber racquetball, right? Has very little shininess to it. It's very flat. On a ball like that, on a form like that, these would be the main parts of the light that you would notice. And unless you must portray a particular material, really nothing else comes up. But just to quickly allude to what happens if you have a different kind of material, not something matte. Basically, you will have a true highlight, that is to say a specular highlight, which is not going to be just right at the top where the light is hitting most directly. The lightest light of the light shape, which we're going to have to, again, pick some vocabulary here. Let's call it not the highlight, right? Because that gets confusing. I tend to think of this as the center light, but we can think of it as the light or the upper light, right? The upper light on this form is going to be where the photons of light are hitting the form most perpendicular, most flat on, with the least turning, right? Here, there's the most turning, so things get darkest. Where things are the most flat on, where the photons are hitting on, that's going to be the most light, right? Those planes have the least change for the most number of photons in that area. They're going to reflect the most light. So in a perfect side view of a sphere, that point would actually be like right on the edge of the silhouette of the sphere. So we can call we're going to call it the upper light. But our vocabulary fails us here. Art teachers have not been able to agree on what to call this. Other people call it the center light. And most dangerously, a lot of art instruction refers to this as the specular highlight. It is not. This is not the position of the specular highlight, right? So we're going to call this the upper light / highlight, which is probably what you've heard the most. But most art education confuses the highlight with the specular light. They are different. So in this case, highlight, upper light, is going to be where the light photons hit the shape most directly flat on. The specular reflection is something different. Specular means mirror-like. The mirror-like reflection is the hot, glistening reflection that you are used to seeing on something like a car. The specular reflection does not occur at the same point as the upper light / highlight. They're actually two distinct things. They get blended a lot because, as we know, values are very compressed in the light. So it usually ruins a drawing to show enough value in the light to differentiate the extremely subtle value change between the upper light and the true specular reflection. So generally, they get blended together, but they are indeed separate. The specular light occurs, I'm going to push this up for a moment. The specular light instead occurs where there's a scientific rule for this. I believe it is where the incident angle and the reflected angle of a photon are equal in respect to the surface normal proper. It's something like that, but only a diagram could explain it. So let's say this is your eye, and you are looking down at a sphere on a table. So you're looking down at a sphere on a table. Now this is a different setup than what we have here, right? I'm going to draw a different lighting setup because this is clearer for explaining what a specular reflection is and where it happens. So let's say this is like a billiard ball or a metal ball. This is a very shiny ball. And a different light situation. We're not having the light directly from on top. Let's say there is a directional spotlight at a 45-degree angle here, or, well, I didn't measure a 45 degrees. So let's just say that the light is in the same position, the same angle to the ball as our viewpoint is. So what that means is that the light is going to shoot a photon down here, hit the ball at the top, and then it's going to bounce back that photon to our eye, and we are going to see, well, we're going to see. Notice that if I draw a dividing line down the sphere, this angle and this angle are equal. They are the same degree, right? Not actually, there's no way I nailed it, but you can tell that they're generally the same degree, right? The surface bisects them perfectly, right? In truth, we know that when a photon is bouncing, right? It's not just bouncing perfectly, it bounces in all directions, right? So it's not in this diagram, but from this strike, there are a bunch of photons going off in different directions that do not create equal angles, right? So this isn't a given, right? There's a particular angle where it's equal. This photon that, unlike his brothers, his brothers went at this angle and this angle, and they created angles on this side of the divide that are not the same as this angle, right? This one that did create an equal angle, this produces the specular reflection, and it is at this point that the specular reflection will be seen. The mirror-like reflection. So this mirror-like reflection would contain the properties of the light. So if this light was blue, the specular reflection would look really blue. This is the kind of reflection that you are used to from a very hot reflection on a car. That is where you would see, basically you're seeing the sun stretched out along the shape of the car. It is mirror-like. It is showing you a mirror-like reflection of the light. In this setup, the light is behind the ball, right? The light is not, from your viewpoint, in this setup, the light would be behind the ball, and that would produce a specular reflection right at the top of the ball. So this situation is not that. In this situation that we've drawn up here, the light is right above. A photon that would be striking the ball. So, I drew my spotlight too small, right? Let's say the spotlight is bigger than the ball. The photon that would strike the ball in this situation, such that its angle of bounce would be equal, right? Would make an equal angle as occurred here, would actually be somewhere. That would give you the bisected angle there. So that means that in a perfect, in a light coming perfectly from above on a sphere like this, the specular mirror-like reflection would actually be somewhere here. And if you look at a billiard ball, that's where it is. It isn't, up there. It's always somewhere on the mid-turn of the form because it always has to be bouncing back to the light unless the light is directly from behind you. And then that would produce sort of a strong edge light. So, and then there's other very niche effects that I really just don't think we need to go into here. But if you're interested, you can look up the Fresnel effect. That is a scientific physical phenomena, an optical phenomena that just says that all surfaces, as they approach their edge, their contour in respect to your viewpoint, become much more reflective. So if you keep your eye out for it, you can see it. It's pretty strong. Again, if you look at something like a billiard ball, it's much more remarked. You know, the reflection of the environment as you're looking right on to the shape is much less than it is on the edges. You'll see the environment reflected much more clearly on the edges in the specular reflection. And also, any material that is reflective enough to hold a strong, true specular reflection, as opposed to a strong highlight or center light or upper light, just up here where the photon hits most perpendicular. Any material that is reflective enough to hold a true specular reflection in the light is usually also reflective enough to show specular reflections in the shadow, because it is lit up by the environmental light. So on most materials like that, even on the shadow side, it'll get raised in value and show artifacts of specular reflections. Again, billiard ball is a good example. It just has such a shiny coat to it. If you look at a billiard ball, even with a strong light coming from it, from like on a pool table or something, the shadow doesn't get very dark. And if you look into it, you will see reflections of other billiard balls, the surface of the table, even in the shadow side. So most surfaces that are shiny enough to hold a specular in the light are also shiny enough to have specular reflections, that is mirror-like reflections, in the shadows as well. And we're not going to go into the details of these because they really are not super relevant for our purposes, especially not for just straight shading. These are really more specific optical effects that you're going to want to get from references. They lend themselves more to painting. They are usually not worth your time in a drawing unless you are doing a drawing specifically of like a shiny ball, right? Where you have a lot of room and value range to capture that detail. But if you are interested in these, especially the Fresnel effect, go look that up, check out how that affects surfaces, and keep in mind that there are these more detailed things to learn about the way light interacts with the surface. There is much more to it, but this is the basics you should have in mind. As long as you learn these, and know what someone's talking about when they mention these phrases, you can master shading. So the details can give you some nice pocket knowledge and explain a lot of confusing references to you. But this is all you need to actually produce great shading, great rendering, great modeling. So let us transfer this knowledge now that we have gained from the ball. Let's draw some blobs, some shapes, and show how to apply each of these parts of the light and what to have in mind when you're dealing with something that isn't a perfect sphere.